Okay, now I'm going to go over a topic that might seem like a bit of a diversion, but it's actually going to be a stepping stone into a tool we're going to talk about called quaternions, which is another way of representing axis angle rotations, but that'll be more convenient for showing how to interpolate between two different rotations. So the topic I'm going to talk about as a stepping stone is complex numbers. And you might have seen complex numbers before, but I'm going to go over them again from scratch, and I'm going to show you actually how they're related to rotations in 2 dimensions. And then we'll build up to something more advanced in 3 dimensions. Okay. So complex number. Well, in order to define a complex number, first I have to define something called I. What is I, should you ask? I is defined as a number whose square is equal to -1. All right? So it's just a number that when I square it, I get -1. And that's a little bit interesting because I couldn't pick a real number that had this property, right? If I pick a positive real number and I square it, I still get a positive number. If I pick a negative real number, actually a negative squared is a negative times a negative, which is still positive. So this is a number that does not exist in the real numbers. So I should note, this does not exist in the real numbers. Okay, but this is enough for us to define the complex numbers. Well, a complex number is just made up of a real part. So I'll say here, complex number x is equal to a real part a plus, we call it imaginary part, times I, this special number, where a and b are both real numbers. Okay, so here's my fancy notation for writing that. So x is equal to some real number a plus some real number b as a coefficient times this special number I. Okay? And so then one thing that we can say is that, well, adding complex numbers works exactly like vector addition. If you think of the a as the x component and the b as the y component. So we would say that adding complex numbers is just like vector addition. So for example, if I were to add, 1 plus 3i to -2 plus 6i, then I would get the complex number. Well, I just add the real component to the real component. So just again to say it up here, a is called the real component and b is called the imaginary component. And we add the coefficients of these components independently. So I would say here, okay, 1 plus 3i plus -2 plus 6i, that is just going to be 1 plus -2, so that's -1 for the real component, plus 3 plus 6, which is 9 for the imaginary component. All right, so I'm talking about them like they're vectors. What if I were to plot them as such? All right, so what I can do is plot the real component on the x-axis and the imaginary component on the y-axis. I made a little helper method up here to do that. So if I were to take, for example, this 1 plus 3i. So if I were to say plot complex number 1 plus 3j, actually it turns out, so I'm in Python here, j is what represents that special number. Because we use I for other things in certain contexts, so they use j instead. All right, so here's what I get. Again, I can think of it as a vector where the real components are along the x-axis and the imaginary components along the y-axis, and then I really can interpret the addition of 2 complex numbers as just a tip-to-tail vector thing that I'm used to. Or I can just go back algebraically and say, okay, add the real component to the real component, add the imaginary component to the imaginary component. So that should be very familiar. Okay. But one thing that I want to go through that's slightly different is how we multiply these together. So when we talked about multiplying 2 vectors together, we said, okay, there's a few different ways to do it. I mean, there's a few different notions of multiplication. There's like a dot product, there's a cross product, and also this direct component by component multiplication that I told you is sometimes useful. But for complex numbers, we're just going to follow our nose, like treating them kind of algebraically as sum of two numbers, and then we're just going to FOIL, okay? So let me show you what I mean. If I make a general multiplication problem here, and I say, all right, let's take a complex number a plus bi, and multiply that by a complex number c plus di, what do I get? And so if I do that out, let me make this smaller. Okay. If I do that out, well, it's just going to be FOILing, okay? So I'm going to take the first term here. So, okay, that's going to be a times c, plus the first inner term, that's going to be bi times c. This multiplication is commutative, so I'll just reorder that to bc times I. Then the other inner term, that's going to be a times di. And then finally, plus bi times di, all right? So hopefully you agree with that. So I FOILed this here. I'm just doing the distributive property, multiplication. Now I can look at this, and I can clean this up a little bit, because I can combine the like terms of I here. So I can combine the two I components into BC plus AD times I. All right, so I did that. I pulled those two together. The other thing I can do is, if I rearrange this here, and I write this as BD times I, well, that's BD times I squared, right? And how did we just define I squared? We said I squared is -1. So suddenly this actually turns into negative BD, which actually is a real number. Okay, so this last term times this last term here actually gives us a real number. I can nest that under, with the real part, under some parentheses here. So if I do that and then I combine like terms, the result that I get is this. Okay? So it's AC minus BD in the real component, plus the quantity BC plus AD in the imaginary component. Okay, so that's multiplication for complex numbers. It's literally just following through FOILing. Okay? Okay, now what I want to do is show you that this weird looking multiplication rule here actually has a really nice interpretation when we think about these as vectors, when we construct a very special kind of complex number. So let me construct a unit norm complex number as, I'll say, I'll define it as something, I'll call it r theta, and I'm going to set that equal to cosine of theta, so that's the real component, plus I times sine of theta. Or I guess if I'm being consistent here, I'll say sine of theta times I. Okay. So there's my complex number. And let me just say, okay, that's my first complex number. Let me make another complex number that I'll say, okay, let's suppose we had a vector v equals, so now I'm going to think, now I'm back in vector land. I'm going to say, let me say I had a vector that had, an x component, a y component. X component was x, y component was y. So now let's define some other complex number. I'll call it p equals x plus iy. Okay? So, I'm going to sort of go from an ordinary two-dimensional vector, and I'm going to just represent the same information, but as a complex number. Okay, so I'm going to put the x in the real component. I'm going to put the y in the imaginary component. So let's go ahead and now let's do the multiplication. So now we'll perform the multiplication. R theta times p. Okay? So I'm just going to follow this formula here. So r theta times p is, okay, so A, that's going to be, so let's look at the real part. So that's going to be cosine of theta times c, which is x. Okay, so that's going to be x cosine of theta. And then it'll be plus, or no, actually, sorry, minus. Okay, so b, that is sine theta, right? So this is a plus bi, and this is c plus di. So b would be sine of theta, and d would be y. So that'd be actually minus y sine theta. All right, so that's the real component. And then let's look at the imaginary component. So that would be plus, okay, so b, that's sine of theta times c, x. So that would be x sine of theta. And then finally plus a times d. So that would be cosine of theta times y. So plus y cosine theta. So all I did here was I defined a special vector, special complex number, cosine of theta plus I sine theta, or sine of theta times I. I took a vector, I plopped it in as the complex number, and then I just performed the multiplication. And so here's the result that I get. Whoops, I forgot to put the I on the end. Okay. All right, so I look at this, and I wonder if this looks familiar to you at all. Because if I rearrange this a little bit, I can actually write it as a matrix multiplication. So here's my favorite little 2D rotation matrix. And so if I just do that and apply that to the vector xy, then for x, I'm going to get the dot product of the first row with xy, so it's going to be x cosine of theta minus y sine theta. Well, guess what? That's that, right? That's the real component, the x component. And then if I do sine of theta times x, so could we get x sine theta, plus cosine of theta times y? Well, guess what? That's the imaginary component. So what you see is if you write this particular complex number, I'll think of it as a rotation operator. This is some complex number that if I multiply by another complex number where I've embedded some vector that I want to rotate, and I just do the multiplication, then I'll get the rotation by this angle, counterclockwise. So maybe it'll help if I look at an example. So let's say that, okay, I'll make a vector v. I'll say maybe it's the vector 1, 1 or something. So maybe this is a vector that makes a 45-degree angle with the origin. All right, so I'm going to unpack that vector, turn it into a complex number. So I'll say that's v0 plus j times v1. Okay, so I just put that in a complex number. Let's say I have an angle theta. Let's say that theta was maybe 30 degrees. So that would be pi over 6. It should be pi over 6. Okay? And so I'm going to rotate this thing by 30 degrees. Okay. Well, maybe first I should plot it. So I'll plot, or add this method plot, complex number, p. Let's just make sure that shows up where I think. Okay, so that's my first complex number. And now let's plot the result of multiplying p. So let me make this special vector now. I'm supposed to make a vector r theta, which is cosine of theta plus I. Again, this is I actually in Python. All right, so let me go ahead and plot that now. So that will be just, I can just do this straight up here. I could say p times r theta. That's the multiplication. It's going to go out and do this thing I derived. And there's the result I get. So can we convince ourselves that this looks like rotating by 30 degrees counterclockwise? I think so, right? So this is at an angle 45 degrees. If I were to rotate this by 45 degrees, actually let me do that. If I rotate this by 45 degrees, that's pi over 4. It should actually line up with the vertical here, and it does. Okay, there's a little numerical problems here, but this should really be 0 in the x component, but yeah, you see that rotates me. All right, so I'm able to do rotations like this. That's pretty cool. And so maybe just one more thing I'll point out is that if you multiply a complex number, so let me just look at one more example of this. If theta is pi over 2, or 90 degrees, then this complex number is going to be very special, because the cosine of 90 is 0, so it's not going to have any real component, and the sine of 90 is going to be 1. So it turns out in this case, our rotation operator is just I. So what that tells us is multiplying a complex number by I rotates it by 90 degrees counterclockwise. So maybe I'll just do one more example of that. If I were to take this complex number p and plot it. And then rotate that by 90 degrees. Okay, well, rotating that by 90 degrees, I'll just do out the algebra here because it's pretty simple. That would just be 1 times I plus 1I times I. All right, well, 1I times I is actually -1, so that would turn out to be -1 plus I. And there we go. There's our thing rotated by 90 degrees. Actually, I should... there's a bit of a problem here. I'll fix this before I make the notes. It wasn't showing at 90 degrees. It didn't have the two axes equal. All right, but anyway, so multiplying by I is a rotation by 90 degrees, no matter what your number is. So that's cool. But in general, multiplication by this special number, cosine theta plus I sine theta, performs a rotation. Okay, great. That's the foundation. So I'm just going to have you do a quick little exercise now doing some of this in JavaScript, and then we'll continue on to quaternions.